So given this equation relating t and h together, how do we understand, or at least how do we place units on these coefficients, negative 4.9, 350, and 2? So figuring out what the units on these numbers are might help us to understand what these numbers mean inside of the equation. So a group that worked on 04, how did you come up with these units that we're seeing here for part A?
Okay, so for the first one, they're asking about negative 4.9, and we were able to determine that that's meters per second squared because, well, in my head, what I was thinking was, since t was in seconds, I took all the t variables and made them s, so it looked like seconds squared and 350 seconds. So if you do that, and, well, I don't know where I was going with this.
You're going to go to the meters.
Wow, I really don't know where I was going with that.
You're going in a good direction, I'd say.
I know. I did. Okay, go ahead.
So on the right side, because it's all addition, you have to have all similar value, number values, which would be, to relate to the whole equation, have to be meters, so they can add together. So that's how we got those meters over seconds.
Okay, great. So the thought here is that the arithmetic on the right-hand side, because we're adding these three terms together, in science, in order to add two quantities together, what do the units have to be of those two things? The same. We can't add two scientific quantities unless the units are the same. So that means that this whole first term, negative 4.9 t squared, has to have the same units as this whole term, 350t, and that has to have the same units as this whole term, the 2. And what do all those units have to end up being in the end, according to the left-hand side of this equation? Meters. So because the left-hand side of this equation is measured in meters, that means that each one of these terms also has to be meters, plus meters, plus meters. So actually, I'd say maybe reading from right to left, reading your answers from right to left, makes a little bit more cognitive sense here. Because right away, the observation that all of the terms on the right-hand side have to be equivalently meters tells us that that number 2 at the end is measured in meters. Now what happens with the 350 times t? So taking a step back to this term. Why is it meters per second? The 350 rather.
Well, because, okay, so 350 is the value of the meters, and obviously, since you're looking for meters, what you can do is to get rid of that t, or I guess you could call it the s, you would divide 350 meters by seconds, so that would leave you with 350 meters divided by seconds. And then the same thing for negative 4.9, except you'd be dividing, since the t is squared, you'd be dividing negative 4.9 meters by seconds squared, g squared. And that's how you'd be able to derive the units for that.
There we go. Everyone catch that? So we need the entirety of these terms. 350 times t needs to be meters, and negative 4.9 t squared needs to be meters. But the t's have units themselves, right? The t has the units of seconds. And so if I want 350 times t to be meters, since we know t is seconds, we need 350 to be meters over seconds, so that these seconds can cancel. We want those seconds to cancel in order that we're left with just meters for that whole term. Likewise for the negative 4.9, we need it to be meters per second squared so that we can cancel the second squared that the t squared is bringing to the table. So that the negative 4.9 t squared becomes, negative 4.9 t squared becomes meters in total. And so the negative 4.9 number in this equation has units of meters per second squared, which means what kind of quantity is negative 4.9 probably? What is it measuring? Second squared here. Yeah, this is probably an acceleration. Now, this is speculation on our part, but the units at least give us a clue that this number, negative 4.9, is probably an acceleration because it has the same units that acceleration has. The 350, that's velocity, because it has units of velocity, meters per second. And the 2, distance. So knowing nothing else about physics and mechanics, just doing the dimensional analysis on these three numbers can give us a clue about what the numbers, negative 4.9, 350, and 2 mean in the context of this equation. Let's talk briefly about if we have this equation that relates height to time, how do we get its first derivative? And from its first derivative, let's also get its second derivative. And this funny notation just means that we're going to take the derivative of the derivative. So the very same process that gets us from here to here, the power rule that we learned yesterday, that same process is also going to take us from the first derivative to the second derivative. It's just the derivative of the derivative. So first things first. Before we find a second derivative, we need the first derivative. And you computed it, and I kind of covered it up here. But where did the first derivative come from? How did you find it?
So based on the power rule, which is the exponent multiplied by the coefficient to the power of the original exponent minus 1.
Okay.
So
There's our power rule.
So for negative 4.9, you would do 2 times 4.9,
Mm-hmm.
and then it would be 2 minus 1 of the exponent,
Right. So the exponent becomes 1 now.
and that would be negative 9.8 t. And then for 350, you would do the same thing. It would just be 350 as just plus 350 because
Right.
it's already in t to the first.
Right. This is really t to the first up here. And so when we take its derivative, that 1 comes down in front and multiplies the 350, 1. And then the exponent turns from 1 into t to the 0. And t to the 0 is otherwise known as 1. So we don't need it in there at all. And 350 times 1 is just 350. Or we can use the shortcut that we learned yesterday, that anytime we have a single power of t and we take its derivative, gone. Okay. We just end up with a coefficient out front. What about that plus 2?
It goes away.
It goes away. Gone. Again, we can also cheat and think of that as 2 times t to the 0. And so if we were to take its derivative, the first thing that would happen is that that 0 would come out front and multiply the 2, and suddenly the whole thing is gone. Right? So that constant term vanishes. So there's the first derivative, just using the power rule for each of the two terms. So far, so good? And remember, the first derivative, this is going to come up in a couple other problems we talk about too. What are the units of this first derivative going to be, dh dt? What are its units?
Meters a second plus meters.
Meters per second plus meters? I think I'm just going to go with meters per second on this one. After all, we couldn't add meters per second to meters. So how would we know? If I just ask you what are the units of a derivative, where do the units of a derivative come from? So looking at the original equation, the units are going to be the units of our h variable, and the units of our h variable were meters, which was a height, divided by the units of our t variable, and the units of our t variable were seconds. So anytime you have a derivative, the units of that derivative are the units of the top divided by the units of the bottom. After all, a derivative is a slope, which is a rate of change. And the units of a rate of change, which is a slope, are the units of the rise divided by the units of the run, so the units of the h divided by the units of the t. So units always change when we take a derivative, unless our independent variable happens to be dimensionless, which is rare in science. All right, so the units of this are meters per second, which indicates that probably the interpretation of this derivative, dh dt, is probably that it's a velocity. And in fact, it is, physically. The first derivative of distance is velocity. And so what then happens if we take the derivative one more time? So the derivative of the derivative gives us what we call the second derivative in calculus. What's the derivative of negative 9.8t going to look like?
Will it be negative 9.8 t?
Negative 9.8t to the power 1 minus 1. And so it's t to 0, which is negative 9.8. And what happens to the 350? Gone. It's a constant, so it's done. So there's our second derivative. Now, one of the weird things about the notation that's been used for the second derivative here is that it uses these squares in both the numerator and the denominator. So when we go to talk about units for a second, the units of the second derivative, the units in the denominator are going to be pretty clear. Take a look that we've got really a t squared going on here. And if t had units of seconds, then t squared is going to have units of seconds squared. But Gottfried Leibniz, who was the guy responsible for the notation we're using for the derivative here, was, I think, very shrewd in choosing how to write that numerator. Notice what's being squared is not the h, but rather the d, which represents the change. So this is the second change in h. But h is not being squared. And so the units upstairs are still just the units of h. So when interpreting the units of a second derivative, bear in mind that only the units of the independent variable downstairs are changing. The units upstairs are still the same as they ever were. Still meters. Here. So meters per second squared, which probably indicates that this second derivative of distance represents what kind of quantity? Acceleration, the rate of change of velocity.